Hi everyone. Today we are going to solve some problems about the transfer function and its application on the Matlab script, especially for the first order and second order time response characteristics. Okay, so in the first example we need to solve the time constants with transfer function and comparison of other systems. Okay, for example, we can define the RC circuit in here. R1 50 ohms and C1 is 0.06 farad. Okay, and so we can build the system 1 with the transfer function code in here, just like this one. TF is a function to build the transfer function. In the first parameter we need to give the numerator, in the second parameter we need to give the denominator. Okay, and so R1, and after that if we run the R1 and C1 comma 1 defines to our system. Okay, and so if we run this code, we will have the 50 divided by 3s plus 1, because the 50 times 0.06 is equals to the 3. Okay, and so just remember that R1 times C1 is equals to the 1 divided by tau value. Okay, and so if this is the case, and then we can build the R2 is equals to the 10 and tau 2 can be defined with the 5. Okay, and sys2 TF the R2 and tau 2 comma 1. Okay, and also R3, for example 100 and tau 3 is equals to the 1. Okay, sys 3 TF R3 and tau 3 1. Okay, these are the system. Okay, this is maybe the electrical circuit. This could be, for example, the heating system. This could be, for example, electrical system with high reactivity. This assumption for our system based on its dynamic response. Okay, in order to show this performance we need to create a figure in here, and step function can be used. Sys1 is the red, sys2 this is the blue, and sys3 this is the green. Okay, and grid on must be written in here, and then the x label is equals to the time sec, and y label is equals to the amplitude value. Okay, and also we need to give the legend to draw the constant, time constant 3. This is the RC circuit. In the second place, time constant 5. For example, this is the heating system. Okay, and we can write the time constant equals 1. This is the electrical system. Okay, and so this is the RC circuit. And if we run this code, and then we will have the step is unit step response applied on on this system. First of all, just see that we have 3 kind of response in here. The blue line is the heating system, the green one is the electrical system, and the red one is the RC circuit. Okay, and so we need to compare the DC results based on the time response characteristics. In order to do that, we need to push this right click in here, and characteristics should be examined. Okay, and so we need to first set the setting time in here. This is equals to the 4 times tau value. Okay, And so, first of all, we need to show the system time constant 5 is equals to what the setting time is equals to the 19.6 value. Okay, which means that 5 times 4 is equals to what the 20 value. And then the red one is equals to what the 3, and so 3 times 4 is equals to what the 11.7. But we had some deviation error in here because we could not create the identical system with the theory based of these terms. Okay, and so we will have the some error value in here, not an exact one. And also the time constant is the what is equals to the 1, 391. See that if the time constant is increased and the slower response happens, okay, and the heating system has the slowest response while the electrical system reacts the fastest in here. Okay. This is the basic solution or the basic conclusion about these systems. Okay, so this is our first example. In the second case, we need to talk about the natural frequency comparison and effect on the system. Okay, first of all, we need to define the what mass spring damper system, just like this one. The m1 is equals to the what, the 30, and zeta value, zeta 1 is assigned to 2, and vn1 is equals to the what, the 5, and cs4 is assigned with the what, the tf, m1 is the what, the numerator of these terms, and so which is equals to the what, the gain value of this term, r1, r2, and r3 are the gains, and so we will have the different steady state value based on these communications. Okay, and so we can create what, the poles just like this one, the 1 s square 2 w1 times zeta 1, okay, and omega n 1 square. Okay, this means that we have the transfer function in here, m1 divided by s square time plus 2 times wn1 times zeta 1 times s plus wn1 square. Okay, and with the same idea we can copy of all of these things in here. This is the m2. We can set the different zeros values in here, and zeta 2 is equalized to 2, and w2 is assigned with what, with the 2 value. Okay, and so this is the 5, and so 2 2 2 and 2 is assigned. Also we need to give the what, the other parameters in here, m3 10 2 1. Okay, and so 3 2 3 3, and this is 3, this is 3, and this is 3. Okay. 6. We can copy off all of these things in here because the same idea is applied on this system, but the 4, 5, and 6 should be given. Time amplitude is the same, but in the first place the natural frequency nf is equals to the what, to 5 rad divided by sec. Okay. And in the second place we have the 2, and in the last place we have the 1. Okay, and so if I rerun this code, and then we will have this kind of response in here. Okay, first of all we need to check the settling time of this system. Okay, so in the first place the settling time is equalized with what, with the same zeta number. Its settling time is 3, and the other one 7, and other one is the 1. Okay, and so if we use the what, the higher radian second, in the natural frequency, we will have the faster response of these values. Okay, and so our conclusion is that higher natural frequency result in faster oscillation, and the system with a natural frequency of the 5 radian second responds quicker compared with the lower frequency values in here. Okay, this is the comparison of the R system parameters. Okay, this is representation of the difference between the natural frequency characteristics. And so just see that we have the different amplitude values in here, just like this one. Okay, which means that we have the different gain values or the steady state values based on this information. But we will talk about it in the later. So in the third place, we need to give the comparing the damping ratio on the system. Okay, for example, the R4 is equals to the 60, and zeta 7 is assigned to 1, and VM4 is equals to the 1. Okay, and then the sys 10 can be assigned with the transfer function of the R4 and s square 2 times zeta 7 times Vn4 comma Vn4 over 2. Okay, and so we can create the more Q system in here, just like this one. This is the R5, this is the 70. For example, this is the zeta 8 0.5, and Vn5 is assigned with the with the same with the previous case. Okay, and also this is the sys10 and sys11 R4, and this R5 should be difference 8, 5 and 5. Okay, and so this is the R6, and we can assign the 80 value, and zeta 9 this may be equals to the 5, and Vm6 equals to the 1. Okay, and so R6 zeta 9 Vn6 and 6 can be given in here. And also we need to copy of these terms just like this one. Okay, and so sys11 12. Okay, and so this is the 10, 11 and 12, and zeta is the first of all the 1 in the second place 0.5, in the third place equals to the 5. Okay, and so if we rerun this code, and then we will have the different characteristics in here. First of all, we need to check the settling time of these terms. The settling time, just see that in the green line, in the zeta is equals to the 5, it's equals to the is 40, around the 40 values. Okay, and if zeta 0.5, and so the 8.08, and the zeta is equals to the 5.83. Okay, and so we don't have any critical nomination or the corresponding information about the settling time in here. Okay, because the settling time is equals to the 4 divided by zeta times Wn, and so if the zeta is increased in here, and then we will have the more settling time response, but before the before or smaller than the 1 values returns to the this one. Okay, and so the most effective zeta values is equals to 1, because our formula is that the 4 divided by zeta times Wn, which means that if the Vn is equals to each other, and so this zeta value, if it's bigger than 1, and so we will have more settling time. But If it's smaller than zeta is equals to the what? Is equals to the, for example, 0.5, and so we will have the long response in here, okay? And so, another case, if the zeta is equals to the 1, this is the critical damped system, which means that we don't have any overshoot value in here, just like this one. If the zeta is smaller than 0.5, which means that this is the what? This is the underdamped system. We can have the what? Oscillation behavior on this time, okay? If the system is overdamped, and so we have the slower response to reach the steady state value, okay? And so if we design the system, we should use to what? To zeta is around to what? It is 0.8 to 1, right? Because if we use these values, and so always we have the what? The overshoot values in here, just like this one. For example, if we choose the what? The 0.5, and so we can use the what? The 0.8 in here, 0.8, and so if we rerun this code, I'm sorry, it's the last case, 0.8, and so we can reanalyze the system just like this one, okay? The setting time is slower at the zeta equal 1, 0.5, 8.08, but in this case, the zeta is 0.8. See that we have the slowest or the smaller setting time in here, okay? But we can also see that we have the peak response in here. Just see that if the zeta is equal to 0.5, and so we have the overshoot values of the 16.3, okay? This is around the what? This is around the steady state value overshoot, okay? And so we have this kind of difference between the what? Between the steady state and the maximum amplitude value. And also, we have the overshoot value in the zeta 0.8, which means that 1.52, right? But if our system is equal to the what? Critical damped system, just see that we don't have any overshoot value in here, okay? This is what the comparison of the our damping ratio change in the R systems, okay? Also, we can see or define to what another property in here for step response characteristics. For example, we can define the sys Q1 is equals to TF, 10 is our gain, and 1, 5, 6, which means that we have the S square plus 5S plus S at the poles, okay? And so we can figure this step signal in here, just like this one. We can apply the unit step signal to this transfer function, and we will have this kind of parameter. Just see that this is the what? This is the settling time. It's given in here around the 2.43, and so we have the peak response in here. Overshoot is equals to what? The 0 value, which means that it's equals to the what? It's equals to the either critical damped system or the what? Over damped system. And so if we evaluate the graph of these terms, and so we can say that this is the over damped system, okay? So we can reach the what? The information about this step signal time response of this characteristics, because it's our system defined in what? The transfer function or the Laplace domain. And so if we apply the step just like this one, and then we can have the what? The time characteristics values of this term, just like this one. And so if we run this code, and then we will have the what? The rise time, for example, 1.41 transient time, 2.47 setting time, setting mean, setting max, overshoot, undershoot, peak, and peak time is given on this graph. And this is the useful information about what? How we can track the R system, or how we can optimize or improve the R system response in the what? In time response characteristics, okay? You can use this function either Okay. In the fifth case, we should utilize the effect of the system gain on response. Okay. So, for example, the K4 is equalized with the what 2, and C is 16 TF K4 1 2 1. Okay, these are the first system, and in the second system, K5, and this is equals to 5, this 17, and this is the 5. Okay, and also 6 18, and we can assign the 10, and this is equals with the K6. Okay, so in order to draw these things, we can copy off these functions in here and uncomment the 16 17 16, okay, 18, and also the gain 2, right, and this is equals to the 5, and this is equals to the 10. Okay, and so how the R gain affects on the response or the time response of these systems. Just see that. First of all, we need to show that we need to understand that the increasing system gain results in a proportional larger response amplitude in here. Okay, and so otherwise we should check what the peak response characteristics in here. Just see that. In every time the R overshoots 0 0 and 0, the R steady state values is equals to what the peak time response, which means that we don't have any overshoot values in here. How about the settling time? Just see that the settling time in every case is the same, because the R zeta and omega n value are equal to each other at each system, which means that we have the same characteristics or the same time constant values on the what on these signals. Okay, but the higher gains can result in increased overshoot and a faster response in here, but the settling time are equals or equal tau value are given in here. But just see that if we use the what the gain 2 5 and 10, see that, for example, at the values of the 5, for example, we have the 2, or if we are using to what the t is equals to the 2, or the first system gain 2 system is around 1.2, but the other system is equals to 3, and the other system gain 10 system is equals to the 6, and so we can have the higher response, higher gain response on the what on the same time value on this system, but the settling time are always equals with the same overshoot ratio values of this system. Okay, so what about the 6, the effect of adding zeros on system response? For example, sys 19, the TF is assigned 1 5, this is equals to s plus 5 divided by 1 2 5, s square plus 2s plus 5. Okay, and also this is equals to the 20, and we don't have the, for example, any zeros in here, just like this one. And after that we can check the what these values, uncomment, and 19 and 20 grid on, and the first system is equals to the what with 0 at -5 and without 0 value. Okay, and so if we run this code, then we will have the two different response in here. First of all, we need to say that adding zeros to a system can introduce faster initial change in the response. Just see that, right? We have the setting time in here, or the transient time can be given in here, just like this one. So we have the faster response in the what? In the zeros. And the presence of zeros can alter both transient and the steady state response characteristics. Just see that. We have the different amplitude, different steady state values on this property. Or we can have the what? The 5, for example. This is also 5, and this is 1, and 5, 5. Can also be added in here. In the second system, we have the two values, but just see that this is the two zeros, and so the same response is given in this system, right? The blue system have the faster initial change in the response of these characteristics, okay? But in this case, we will have the what? Higher order system characteristics, which means that the steady state is equalized at this case. But if I choose to remove these terms, and so just see that the first system, if you don't have any without zeros, any zeros, and so the steady state is changed. But if we have more two zeros in this system, and so the steady state is equalized at the end of this code. Okay, so these are the Matlab session guide, and so these are the useful information about the Matlab codes in order to what? In order to build your system on the what? On transfer function domain in terms of the what? The zeta and wm value, or the tau value. And so we can easily analyze the what? The effect on the any system response on the what? On the Matlab simulating program. Okay.